Chemistry is kind of the hardest to wrap your brain around, but we're going to walk through it, and I'm going to try to walk through it as clearly as I possibly can. But this is where we get into the part with cells, potentials, and electrochemical cells. First thing we have to do is look at the units associated with electrical work. Now, one that we will use when we do electrolytic cells, both in lab and later in the chapter, is Coulomb. That is the quantity of charge that flows past a fixed point when 1 ampere flows for 1 second. The one we're going to use the most is the ampere, which is 1 coulomb per 1 second. And a volt ties it into the work that's done, because we're dealing with it in joules, as 1 joule per 1 coulomb. So it's the work done, 1 coulomb of charge moves through a potential difference of 1 volt. Sounds like a bunch of what, where, when, and hows. Okay, we're going to use amperes the most. We'll use coulombs a little bit, but more about that when we actually get to using it there. But right now, just remember that these are the units that are associated. Now, how is cell potential determined? The E cell, or the potential of a cell, is the electromotive force. It's the difference in the potential of the two half cells. Now, this is where old school meets new school, and I'm old school, and I prefer using this. E cell is E red plus E ox, because remember, you always have to have reduced and oxidized. This is the new way of doing it, and by new, that could be 15, 20 years, but remember, I'm old, and back in the dark ages when I went to school, we used the other. Now, I'm going to tell you why I prefer this. To me, is makes more sense. The other is a negative on a negative, and that drives me crazy. Now, the difference between this form and this form is, remember, this is standard. We'll do standard cells and we'll do non-standard cells, which are known as Nernst cells, but more about that in a minute. Remember, standard conditions for thermo and electrochem is 25 degrees C, 1 atmosphere, 1 molar, etc. Okay? So, E red plus E ox, these are the same things. This is actually E ox, and this is E red. The difference is that in mine, I go ahead and flip the signs. In theirs, you put a negative on a negative. So, let's talk about standard reduction potentials. They are determined by way of a standard. For example, New Orleans is below sea level. Denver is above sea level, because sea level is your set point. Well, in electrochemistry, your standard hydrogen electrode, or your SHE, is your standard, and it has a voltage of 0. By definition, just like when we did acids and bases, where we always wrote the neutral species, everything is written as an E red. Okay? If you need oxidation, then you reverse the reaction and the sign. So E ox is equal to E red. So if your E red is equal to negative 0.25, then your E ox is equal to positive 0.25. If your E red was positive 0.25, then your E ox becomes negative 0.25. So you just flip the reaction, flip the sign. The more positive the E red, the more easily reduced. The more negative the E red, the more easily it is oxidized. Under standard conditions, species higher on the table will oxidize species below. That's when it's listed by E red. I list it alphabetically because I'll show you one where it's listed by E red, And you'll notice that iron may appear 4 different times all over the place. And it's really hard to look at it that way. So I've done mine alphabetical order because it's easier to view. E cell is a function of nature and concentration, but not quantity. So unlike most of the other things we've done where if we multiplied the equation by 2, we multiplied the value by 2, that is not true. It doesn't matter whether you have 1 mole or 52 moles. It's not going to change the E-red value. And that one's a little counterintuitive to everything we've told you, but that's true with electrochemistry. Okay, so here's our table as we have it here where we start with the highest E-red and we go to the lowest. And if you'll notice, we have iron here and we have iron here. So you may think, oh, iron only appears once. No, in this particular one, it appears more than once. And it's not just iron. Here's oxygen and here's oxygen. Wait, and here's oxygen. So wait, oxygen appears 3 times. So which one do you use? Okay. Well, you use based upon a variety of things. The first thing you've got to keep in mind oftentimes is, are we working in an acidic environment or a basic environment? Because this one's acidic, this one's basic, and this one's acidic. Why do we know? Because that's an acid, that's a base, and that's an acid. And this one doesn't care. So sometimes you can pick and sometimes you can't, and sometimes you need more information. So don't sweat the small stuff, because I've posted this in D2L. But if you'll notice, and I'll pick on something that's in here. These are all of the gold ones that I have. 1, 2, 3, 4, 5. There are 5 here. But instead of having to go all over the place and say, well, does this have gold? Does this have gold? No, they're all together now. Because just like KAs and KBs, they're huge tables. So this is actually 2 pages. So when you print it out, you can print it front back, or you can have 2 sheets. Now, as we work the following problems, you want to go ahead and have these printed off so that you can view them, because I am not going to keep popping back and forth to look at the table because I already have them written down. Okay, let's start working with problems. When you work with problems, galvanic and voltaic cells must be positive. That means if E cell is greater than 0, positive is spontaneous. If it's less than 0, it is non-spontaneous. So if I ask you whether the reaction will occur, if it's non-spontaneous, E cell's negative, the answer is no. Okay? So when using the electrical potential chart, answer the following. Is H2SO4 capable of reducing CO2? So we're saying that CO2 has to be E-red. That means that H2SO3 has to be E-ox. Okay, so if it's got to be E-ox, you need H2SO3 found on the product side. Whereas the CO2, we need that on the reactant side. So if we go look it up, we'll find out that E-red is equal to minus 0.49 volts for CO2. Whereas if we looked it up, we find out that E-red here is equal to 0.20, which means E-ox is equal to negative, 0.20. So if we add E-ox, E cell is equal to E-ox plus E-red, then that's negative 0.20 plus negative 0.49, which is negative 0.69 volts. That's a negative, so it is non-spontaneous. So the answer is no. Okay? It's as simple as that. Now, the other way to do it is E cathode minus E anode, which is the same effect as identifying EOX. Okay, and if you prefer to do it that way and it works for you, then go for it. I find, because if you're doing it the other way, you have to identify the cathode and the anode, which means you have to identify which oxidized and reduced. And then you have to find the values and put it in as the negative, and I find positives easier to deal with. So, all right, so if we're looking at this one, is dichromate capable of oxidizing? So that means this one's oxidized, which means this one has to be reduced. Okay. So we find out that the value of E red for dichromate is 1.33. Okay. Now this one also happens to be acidic. Why is that important? Because if that's acidic, then we can't have a reaction in a basic. We can have it in neutral because that means it'll take acidic. So if we look at the oxidation for here, again, that means that the manganese 2 plus has to be on the product side. So we find E red, we have two values. Okay. They both happen to be in acidic environment. So we can get EOX as either negative 1.23 or we can get it as negative 1.51. So you're like, okay, wait, what do I do now? So if I add these two, I get E cell equal to positive 1. So yes, this one can do it. If I do this one, okay, and remember this one's a negative as well, so we end up with 8 negative 0.18. So this one is non-spontaneous, so the answer for 1 is yes, the answer for 2 is no, and since they're both acidic, if you put them in solution and let them both go, one of them would go. The other one wouldn't. If you've got them different, then you don't know. So the answer here is a function of which values you pick. And don't freak out on me because you're going to have the values that I give you. And if I restricted it to where I only gave you 1, then that means that you had no choice in your choosing. Okay, so let's take this a step farther into a bigger problem, and we're going to look at the values in the answer share. Now, I know I have a video of this, and I know I have an extra problem with this, but I will double check because sometimes what I know is really not what I know. But given the entire following solutions like this, and you're going to have one like this on the test, this puts it all together. So you're like, what do I do with this? Okay, well, there are lots of things you do with this. So let's start, but I'm going to put everything in as E red only. That means that we can flip things at will, but we also have to put in a directionality. So, for example, if you look at your table, CE4 plus is going to CE3 plus with a 1.61 voltage. But it has to go that direction because if it goes opposite, then it's a EOX. We don't want to go there. And we have iron 2 plus, 3 plus, and iron metal. And you're like, oh, we can use all these. Nope. Iron 2 plus goes to iron with 0.440 volts. And iron 3 plus goes to iron 2 plus with 0.771 volts. Magnesium 2 plus goes to magnesium metal with at negative 0.2556. Okay. Nickel, wait a minute. Nickel metal, it's not on the list, but we can take nickel 2 plus to nickel metal at negative 0.257 volts. and we can go from 10 2 plus to 10 metal at a negative 0.152 volts. All right, before we go any farther, you need to take a second and compare this to the chart and make sure you understand where I got all these numbers, because it's going to be real important that you know how to use them. And because that 7 looked bizarre, we're going to put it back in. Okay, so once we've got those values, then we're good to go. All right, the question is, what is the strongest oxidizing agent? Well, if it's an oxidizing agent, we're looking at E red. So that means we want the largest E red. So when we look at our table, the one who has the largest E red is over here, cerium 4 plus. Now somebody might say, oh look, magnesium 2 plus is greater. Yeah, but it's negative, so you can't pick it. Okay, so which is the strongest reducing agent? That means that it's going to be the largest E-ox, in which case smallest E red. Now again, in this case, you're like, wait, I got that negative 2 point whatever. That's true. Well, we don't want the magnesium 2 plus, we want the magnesium. We cannot use the magnesium 2 plus because it has to oxidize. 2 plus has already lost its electrons. You can't lose any more. So you can't do oxidation on 2 plus. You have to do it on the magnesium metal. Okay, the question is will iron dissolve in a 1 molar solution of cerium 4 plus? Okay, iron dissolving, that means we're going to go from the solid to, in this case, the only one that'll go there is 2 plus, the aqueous form. That's dissolving. That means this one's E-ox. Which means if it's E-ox, then we flip the reaction, we flip the sign. So we get a positive 0.440 volts. Plus, that means that if that's E-ox, this one has to be E-red, which is 1.61 volts. So 1.61 volts is equal to 61, that'd be 0.5021. Okay. Do we have to actually do the math? No, both of them are positive. We could say that E cell will be greater than 0, so the answer is yes. So that levels our playing field for that one. Okay. Which species, so for D, which species can be oxidized? So we're looking for E-ox, and we're using H plus, so it has to be E-red. Now E-red here is 0. Okay, so that means E-ox plus E-red has to be greater than 0 to be spontaneous. So if E-ox plus 0 has got to be greater than 0, then E-ox has to be greater than 0. So we need anything with an oxidation greater than 0, or if you want to think of it this way, any negative E-reds. So if we look at it, we can't use cerium. Okay, we can't go from cerium 3 plus to 4 plus. Yeah, that's a negative, but that's an E-ox. So we're only looking at the numbers we have there. So that won't work. Oh wait, iron 2 plus to iron is reduced. So if we flip it, that means that iron can be oxidized. Okay. Then we've got manganese to magnesium is a negative R, so that means magnesium can be oxidized because magnesium 2 plus is the product. Now, we can go from nickel to nickel 2 plus, but this nickel's not on the list. Okay, is not on our list. We can have it go there, but we can't come back from there, whereas we can with the tin because it's on our list. Okay? So, then which species can be reduced by hydrogen? Okay, so if um, if it's oxidized reduced, then that's E-ox. Then there's 0 here. Okay. And this is in acidic. So basically, if E red plus 0 has got to be greater than 0, then E red has got to be greater than 0. So that means that anything that's positive E red, so that'd be cerium 4 plus, iron 3 plus, but not iron 2 plus. No on the magnesium, no on the nickel, no on the tin. So we're done with that one. However, there's a little bit of a twist on that one. I'm going to add a page if I can figure out how to do that. Okay. So if we're looking at these species again, and we're told that which species can be reduced by hydrogen. Okay, same question, but now we did it in an acidic. If it's in basic solution, then the E-ox is equal to plus 0.828 volts for hydrogen. So E red plus 0.828 it's got to be equal to 0, greater than 0. So E red is any number that's greater than negative 0.828. So in that case, if we go back and we look at our species, then if it's greater than a negative 0.8, cerium will work again. Iron 3 plus will work again because it's positive. But now iron will work. Magnesium still won't work. But now nickel will work. So then our answer changes. The species in a basic environment that can be reduced would be cerium 4 plus. Your usual suspects that worked before will work again. But now we can add iron 2 plus and nickel 2 plus to the list. So, how do you know which one to use? On a test, I tend to restrict you, but if you're not restricted, you have to give both options. Okay? So, simplifying it again, will aluminum metal react with 1 molar tin 4 solution? If so, what is E cell for the reaction? Okay, aluminum metal, that means we've got aluminum going to aluminum 3 plus, which we know is an E-ox. Okay, and for this value in acidic, we get 1.676 volts for acidic. And there's a different value for basic, 2.310 volts for basic environment. So 1 molar tin, if aluminum is being oxidized, tin 4 has to be reduced. So in the case of tin, the E red, there's only one value and it's 0.154. So again, E red plus E-ox is got to be greater than 0 if it's positive. Okay, if it's equal, it's at equilibrium. More about that one later. So you have two options, 1.676 plus 0.154 is equal to 1.830, and 2.310 plus 0.154 is equal to 2.464. So in both cases, yes for both. So this one's a yes and this one's a yes. So in both cases, the answer is yes. So in this case, it didn't matter. Do you have to work the math here? No, if both of them are positive, then it's going to be positive, so you don't have to work the math. But I like to work it just to help. What about a 1 molar solution of cadmium oxidizing metallic copper? So we're going to oxidize metallic copper, which means that we're going from copper to either copper 1 plus or 2 plus, whatever is on the chart. And then cadmium over here, 2 plus, is going to have to be reduced to the cadmium metal. Okay, so this is E red, and this one is E ox. So for cadmium, the E red is equal to a negative 0.403 volts. And for the copper, the E ox is either negative 0.340, or there's a second one. Actually, I found a third one. Negative 0.520, and there's a third one, or plus 0.36. All right. So if you add E red plus E ox, none will be greater than 0, so no. Okay. The one close would be the negative 0.403 plus 0.36. That means it's 340 negative. It's still negative. So they're all negative. So the answer is will this reaction proceed? And the answer is no. Okay. Now, one other thing that you need to be aware of, that you may have heard the phrase the activity series. This is where a solid or more reactive metal will displace ions of less reactive metal, and it's based on potentials. And so if you look at the activity value, that these metals here will replace these metals here. So it is easiest to oxidize here, easiest to reduce here. This is actually very important if you go into electrolysis and metallurgy usages. One of the things that we've talked about was catalytic converters, and you use platinum, palladium, rhodium. These are really high dollar metals. And so there's a huge industry where they recycle and regain these materials out using electrolysis. And if you're bored, look up on YouTube or anywhere else, electrolysis, the how it's made does them on the History Channel, etc. But you'll see these huge electrolysis tanks, and they're using the activity series to remove the metals.